Yeah.
I made the third one, so I'm trying to put figures in the lecture. After third, I still have to put figures in the second. So I can give you the third after class now, or I can give you the second and the third tonight just in one file. Do you want separate files too? I think separate files. I can give you the third right after this. The second one, yeah. So it just doesn't have the figures in it. So I want to put the figures inside.
It's all it tastes like, dude.
A couple of them.
I'm sorry.
One is, you'll notice on the schedule there's some slots that are called student activities. So these are slots that, as the name implies, in one part is for students to self-organize into seminars, tutorials, or whatever you prefer that has to do with the scientific part of the program. Or, in particular, maybe ask us one of the lecturers to give a tutorial or maybe some elaborate or have some kind of a recitation session or something like this. Basically to accommodate, last minute adjustments that we need in the schedule. So I encourage you, to organize and use those slots for organizing student activities. Second thing is we have the poster session coming up tomorrow night. So you poster abstracts that you sent in are posted on our website. So check out, make sure your poster abstract is appearing there properly, and figure out which session you're in. There'll be 3 poster sessions through the 4 weeks. So tomorrow night is the first poster session. So if you're on the list of the first poster session, it's basically just alphabetical. Then be prepared to give your poster. We'll put them up in the afternoon. We'll have the room available, so then you go maybe after lunch. You'll put up your poster, and then session is, I believe, is at 7. 7 to 10, yeah. And we'll have some drinks there. And there was something third thing I was going to say, but I'm missing it. I'll catch you next. But without further ado.
Okay. Okay, so what we want to do today is finish up what we arrived to yesterday. That's for the first part. So just to remind you,
where we're at, we're supposed to be able to parse out everything that's written here, although it's a mess. The three equations up here, I'll call the compatibility equations, and every time I will write two fundamental forms, A and B. This is the metric of a 2D surface, and this is the curvature form of a 2D surface. I'm going to assume that they satisfy this. Essentially, these set of equations are the source of all nonlinearities in the system. And that is because the Hamiltonian we have, or the energy we have for this system, is quadratic in A and B. What's written here is that the total energy, or here the energy density, has two contributions. One comes from stretching, and that is from compromises made in the 2D metric. I'll give you a reference metric. If you're not matching that completely, there's going to be some penalizing of that, and that's linear in T. And there's a cubic in T contribution, which is the bending contribution, which penalizes mismatches in the curvatures. I'll give you some group of reference curvatures, and if you don't satisfy those, that's how you pay for it.
Alpha, beta, gamma, delta is a 3D elastic.
It's 2D. Yeah, Greek indices essentially take the values 1 and 2. We're in the two-dimensional realm here. And this thing here, the coupling of these tensors, is made... Oh, sorry for having A here and G here. This should all be A bars. This is the inverse metric, which is the reference metric of my 2D manifold. Thank you. So this is a typo. They're all A bars. And so those of you who are tensor notation savvy can see that everything here is a true scalar because I'm contracting everything appropriately. And having noted that, from this point onwards, I'm going to be sloppy. And I'm going to say that the stretching energy is linear in T, and it's a square in the metric difference. And the bending energy is going to be a T3rd B minus B bar. And you should understand these as those, where A and B, of course, satisfy these nonlinear equations. T is the thickness of the material.
Okay. And why should it be, I can imagine if I make we're talking about surfaces being embedded in leaves and that sort of
Yes.
thing. So why do I have exactly the same tensor in the stretching as the bending? If I have strange constituents, then I can make those different. Just like you're saying, the ratio is exactly
So
3 times T squared, for example.
yes. So
That's surely not true in general.
it is general if they all come from an isotropic
An isotropic.
elastic media, which was three-dimensional. So
Made it up a bunch of rods. Had a bunch of rods that were compactified into
a bunch of rod, a stack of non-identical surfaces, for example, all of these would give you different results for these.
Thank you.
So the underlying assumption is that we draw these from the isotropic uniform elastic description we had previously for frustrated 3D objects. Only now our frustrated 3D objects are thin. So we want to describe them as surfaces. So these are the underlying assumptions. Thank you, David, for noting T is the thickness. And there are details for this thing, and I want to go through the details and understanding of what this thing does through an example, because I think that's the best way to do it. So our example can be realized in a lab using hydrogel. So I prescribe some A bar and I prescribe some B bar, and then I ask what does the thing does. And I can do that in a variety of thicknesses, which I control by the spacing between those plates. Here's a result of an experiment. This is the metric I'm going to prescribe. A bar, the reference metric, is 1, 0, 0 sine squared of x1. The reference Gaussian curvature that corresponds to this is 1. So this would like to assume it has the metric of a spherical dome-like shape. I'm going to give it a trivial reference curvature. That is saying all different laminas, all different horizontal sections of these things behave the same. It doesn't want to bend up or down. Well, what does it do? What we see here is the result of an energy minimization of the energy versus the thickness. Each and every one of these guys is a different realization of these two geometries, okay, for a different thickness. I could realize it in a very thick slab, or I can make it very, very thin. What do we see here? It's a log-log plot, and it has a linear in the thickness section and something that asymptotes to something that is cubic in the thickness. How do we understand those? So if we're very, very thick, this becomes very, very expensive. And that is a general thing when you have thick slabs. So this would correspond to the moment of inertia that we heard about from Alex. When we have thick objects, it's very expensive to bend them. A thick slab would just solve the plane strain problem. It would do the compromise it has to do while keeping itself in the plane. So all the different realizations here are identical in the 2D sense, they only differ in their thickness. So this is an unbuckled state. As we make our object thinner and thinner, bending becomes increasingly more accessible, and stretching becomes more and more expensive. In the infinitely thin limit, and one can prove this mathematically, you approach an isometry. You're going to satisfy completely everything that is given here. And then this does not determine the surface uniquely. You have to say, well, which of the isometric realizations of this guy am I going to choose? And you choose the one that minimizes the bending energy. This is this guy. This is the bending energy minimizer amongst all isometries of the prescribed metrics. Yes? Exactly, yes. Okay, now there are two limits. There's the group of metrics that you could realize with finite bendings, and this is the group I'm talking about. You are correct in noting that there's a subset of groups of metrics that you cannot realize with finite bending energy, and those will behave differently. So thank you for noting that. In order to have this behavior, I have to have some candidate in which I can set this guy to 0 and have a finite contribution here. So only in that setting, but that setting is actually fairly large. You have to induce pathologies in order to avoid it. This A bar can be realized isometrically without any problems. That's so the metric of a cone. It's fairly trivial that you can show that it has a 1 over r curvature here in every isometric embedding of it, and that would give you a diverging, logarithmically diverging bending contribution. And that would be pathological for every isometry. So you'd have to compromise it somehow, and you can see that that gives rise to different scaling behavior. Yes? Mm-hmm. Yes.
And so when you said that defining the beam was for every layer, what do you mean by layer in that sense?
Our object is indeed 3D. It's thin, but it's three-dimensional. So it's not really an idealized surface. An idealized surface is just the way I would like to describe it. So as a three-dimensional object, what gives rise to curvature is structural gradients across its thin dimension. What I do when I describe it this way is I describe it as different laminas. Each of those is an idealized surface, and now I stack many of them, one on top of the other. And then in my head, I can think of each of them as structurally different or identical, giving rise to no curvature. Okay, so the transition between the flat state and the branch that attempts an isometry occurs via buckling. It's a forward pitchfork, everything you would expect. But it's a very abrupt transition. Immediately after that abrupt transition, you have a slightly buckled state. And as thickness is increasingly reduced, you approach the isometry, which minimizes the bending energy. We can rewrite this bending energy, which is a scalar composed of the inverse metric and the reference curvature and the curvature, because this guy is 0, how many scalars can we construct for a second order scalars can we construct from a 2 by 2 matrix? 2. What would they be? Okay. For this guy, B alpha, they're all wet. B alpha alpha is just 2 twice the mean curvature. Whereas the determinant of B, and when I do that, I of course mean an upper index and a lower index, gives you the Gaussian curvature. So you can express all the bending contribution with the mean curvature and the Gaussian curvature. This is a familiar form of something which is called the Helfrich energy, which is commonly encountered when we do fluid membranes. Fluid membranes don't have a reference metric. They cannot support any shear. Nonetheless, they penalize bending. This is a different setting. We minimize this elastic energy or this curvature energy with respect to a given metric. We have to obey this metric when we minimize this. Turns out that the solution for this metric is spherical and simple. Now comes something interesting. We had 2 energy contributions, each of them quadratic, and we'd expect them to carry roughly equal amounts of energy. That would still mean that if this and these each populate equal amount of energy, that A goes to A bar faster than this. So you would obtain a vanishing energy contribution for the stretching. Nonetheless, if I now plot the different components we see here, we see that the two obey completely different scaling laws. The bending contribution behaves as t to the third. The stretching energy behaves as t to the 7/2. And this is a pathology that we would always observe when we actually consider different perturbations or different ground states for the two different quantities. What am I saying? The 0 energy level set of this guy are the isometries. They reside here. But the 0 energy level set of this guy is flat. It resides there. And the intersection of these two groups is empty. And when I would like to assess how much energy each of them contains, when I'm doing a variation in the system, then I must perturb a given configuration and not two different configurations. What I can do is say, you know what, at an isometry, the bending energy is going to be some asymptotic bending energy. That's going to be the minimal number this could be, assuming A equals A bar. If that is the case, we're going to mark that by EB naught, and we're going to subtract the given bending energy at a given thickness from EB naught, and then we're actually perturbing the same configuration. We're perturbing the isometry. So with respect to energy variations, we see that each of these does carry equal amount of energy, but we had to actually think of a configuration both of these branches can assume. What is this funny number? Where does it come from? That number comes from a boundary layer these things have, and it has to do with the question of what is thin. I just told you that when these objects are thick, they compromise the metric and they remain flat. And when they're very thin, they obey the metric and compromise the bending. What's thin? What do I compare thin and thick to? So what scales do I have in the system? The elastic constants don't have length scales in them. And this is a continuum description. Okay, so we had thickness, and we have to compare that thickness to something. So size is one thing. I have the lateral size of my system, and I have to compare those two. There's another quantity in the system which comes from the geometry. So it's the curvature scale. So we have, this is a length, 1 over this is a length scale. We have the length scale of our system, and we have thickness. And if the thickness is much smaller than both of these, then I think we can say we're thin. But then something happens. Well, if this is my disk, what happens to a point which is really, really close to the boundary? Does it also think you're thin? What if the object as a whole, let's think it's humongous, is very thin? Its lateral dimension is much, much larger than the thickness. But then I'm trying to consider what happens to a point which is very close to the boundary. And the answer that for those type of points, what we have to consider is their distance to the boundary. And it could just happen that these points would like to behave as if they're thick. Can we see that algebraically? It doesn't really help, huh? Okay. So this is our circle cap. This is too small. This is our spherical cap. This is the isometry. Okay, so this has A equals A bar, and all I pay is in curvatures. What I would like to say is that there exists some length scale L, along which I can compromise the isometry and reduce some of the bending energy the system has. Okay. This W, which is the magnitude of this, is essentially x squared over r, where x is the coordinate along this direction. The reason why it's x squared is because it has zero linear component in here. It doesn't perform a kink. And it's 1 over r, where r is this radius, because I ask it to take this curvature and flatten it out. So it must have a curvature which is 1 over r, which is the second derivative. Okay? So this is how this W behaves. Now I would like to say, how much strain does that entail? So it doesn't necessarily contain a lot of strain in this direction, but along the hoop direction, I dilated the system quite a bit. By how much? Roughly. What was the circumference before? What was the circumference after? 2 pi r plus w. The difference is 2 pi w, which is essentially x squared over r squared, which is like L squared over r squared. This is how the strain looks like. How much bending did we reduce? So the curvature read 1 over r, and now it reads 0. I can make this a flat line. So I didn't do much for that curvature. I changed it by w, which is a small number. But for that curvature, I took something which was 1 over r and made it 0. Now let's make the elastic energy. So delta E stretching is positive, and it's strain squared times area. It's L squared over r squared times L times r. 2 pi doesn't really matter. Of course, there's the thickness multiplier here. the bending energy contribution is negative. You reduce the amount of bending. That's the driver of this whole boundary layer. And what you're able to reduce is this curvature squared, and you reduce it over an area of L times R, and there's a multiplier of t to the third. And what you want is the sum of these things to be as negative as possible. This is now what we're gonna, this is given for us, R is given, T is given. The only thing we can play with is L. We have essentially L to the fifth minus some coefficient L. This is something that looks like this. And we're looking to find this point. The point where the negative contribution to the energy is largest. And we can obtain that by differentiating this. So we have essentially L to the fifth, R to the third thickness. This is this guy, minus L over R. It's 1L, 1R, T to the third. We differentiate with respect to L to find the optimal position. We have L to the fourth times T over R to the third equals T to the third over R, which is saying L to the fourth is T squared R squared. And if we further expand that, this is a point of delicacy. In the sphere, this direction of curvature was R, and this was also R. In the most general case, you can show that L behaves as the square root of T divided by the parallel component of the curvature, which parallel is parallel to the boundary. So we have this overall behavior. When things are very thin, they obey their metric. When they're very thick, they try to obey their curvatures. Those are two distinct limits. However, there's a region near the boundary where always you kind of think you're thick. And this is the size of it. And this is the energy contribution it gives. And this is how it looks. Questions so far? Okay. I just, flipped it inside out. So it could have the same metric, but then its curvature are pointing the other way.
Okay, so
when I'm flipping it inside out. So what it did is it said, you know what, I'm going to give you the metric you'd expect me to give you, except for a tiny area near the boundary where I really want to go ahead and try to keep my reference curvatures. And that's the reason it plays out. Yes, so you can understand the reference curvature as difference in lengths of the different laminas. And now when we come to think of them, everything is 2D. We just have a reference curvature. I don't care where it came from. But you're correct. It comes from the gradient in the reference lengths. Okay.
There's a small range of thickness for this wood.
Around here? Yeah. Yes, if you know of Benny's walk near threshold and extending that too far from threshold, that's the near threshold limit. So this is the backlink transition. You can expand about the bifurcation and get how this area behaves. And surprisingly, the first unstable mode in most systems I know points at a viable isometry. That didn't have to be the case, but I can't think of a counterexample. That sounds topologically challenging.
do a tiny
through a tiny hole. Okay. Okay. Usually when I give you a metric, there's a whole myriad of isometries they can assume, and then what we do is choose between those. A closed bowl is one of the only instances where there's only one. Okay? So if you're a closed bowl, you inverted it inside out, the bowl is thin enough, nothing interesting is going to happen. The object is going to be residually stressed. Its mechanical response properties could differ, but you would only be able to access that through either probing or cutting it up. Okay. For moderate perturbation, it is going to be stable because it can't really access other isometries nearby. However, if you do leave a small hole, so say you have this image, but you get a much bigger angular section of the bowl, you would see this phenomena in the free boundary. It's going to look less pronounced, but you would see it nonetheless. Okay? Okay. So there's a trick I wanted to... I don't have it anymore. I wanted to share with you because I find it very useful, but I think I'm not going to have enough time to write it all out explicitly. Let's use that board. And it looks as follows. It's something which happens whenever your energy decouples to two contributions. So now I'm looking at the energy divided by thickness, and you'll see why it's more convenient in a second. And there's one term which depends only on the configuration. That's the stretching. There's a t-squared coefficient, and another term which again depends only on the configuration. And for every finite thickness, I'm trying to ask what is the configuration which minimizes this mess. I know that there's a limit in which I can set this guy to 0. There's another limit where I can set this guy to 0. Now I have to work with finite thicknesses. What happens? So one thing that happens is that delta E over T, delta R, that's varying the configurations, equals delta E stretching delta R plus T squared delta E bending delta R. So these all should be understood as Fauché derivatives. And let's now make E star the minimizer, the minimal energy at a given thickness. Okay? The same would hold for, so, okay, let's say R star of T is the argument of E star. So you give me a thickness. This is the configuration which minimizes this whole mass at this thickness. And now we say that E stretching star of T is E stretching at R star of T. Is this the minimal stretching energy possible? Only if T equals 0. For every other T, I have to compromise both contributions. For finite T, this is not going to be the minimal possible energy. But when I add this to the bending guy, which is again not minimal, but two of these together are optimal in this sense. Okay. That means that E of t and R star of t is smaller or equal to E of t and any other configuration. So I'm going to skip the algebra now. I'm just going to say that in particular, it's going to be smaller than the energy of the minimizer of another thickness. And similarly, I can say that the energy at the minimizer of the appropriate thickness is going to be smaller than the energy at this thickness with a minimizer of the other guy. And the reason this is going to be insightful is because I have a complete decoupling between the knob in the system, which is the thickness, and the objects that do the optimization, which is the configuration. This will tell me that the minimizer of the bending energy, for example, for t plus delta is going to be smaller than the minimizer at t. That tells us that the bending energy is a decreasing function of the thickness. Now, we knew that when we go to very large thicknesses, it had to go to 0. This tells us it does so monotonically, and it doesn't matter what delta is.
So why can't you put a t minus delta
Up here?
up in the equations at the top? So you say that why does the sign of delta make a difference there?
It doesn't. It doesn't. This would hold. Just when I do it this way, I get two equations which I can subtract, and I get this immediately.
But suppose delta. So it seems that it doesn't have the sign of delta.
Oh, so where does delta come? I'm comparing two terms, so I'm going to make E stretching vanish, and I'm going to have t plus delta squared multiplying on one side, and it's going there's a term that's going to look like this, and it's going to change the sign of my inequality when I divide by it. So if I take t minus delta, everything works out, and the inequality changes sign. So this tells us something. This tells us in particular that as I increase the thickness, the bending energy should reduce. And that is something quite general, and it should hold for any system. It's because I didn't work it out, and we have very little time. The argument is as follows. This is the abstract of it. The algebra is in my notes. The minimizer for thickness t gives you the least possible energy amongst all possible configuration. It has both bending and stretching. And because t is finite, for one of the limiting t, it's not interesting. And now I say, in particular, it has less energy than what would happen if I consider the energy with thickness t, but the minimizer from another thickness. And that allows me to do both of these lines. And when I take them together, it tells me this monotonicity. It comes from this, and it says that as t diminishes, this becomes less significant. Okay? And this becomes more significant. And it turns out that because of the complete decoupling between the configuration and the knob we're turning, then we can say statements that show essentially that this grows monotonically. Any better now?
The argument doesn't.
It doesn't convince you.
Because I'm thinking, what if I do something crazy with the stretching engine?
No, you're not allowed in this, what I'm doing here. It's not for every configuration. It's for the minimizer. Okay? Everything I'm doing here is for the configurations of minimal energy at a given configuration. So this is not the bending energy of anything at a thickness T. It's the least possible bending energy you would get for a thickness T in the minimizer of the full thing. Every time I'm minimizing the full thing. Okay? I'm minimizing both stretching and bending simultaneously. And as I do so, the bending component increases as I go lower and lower in T. This is what it says. I'm minimizing the whole thing, and this guy grows and grows. Okay?
So this means that we can write the same kind of relation for bending energy that you just wrote.
For stretching? Yes, it has the opposite sign. As a matter of fact, if I take this variation and multiply it by R star dot, okay, which is how the minimizer changes when I change the thickness, I get something that looks like E stretching star dot equals minus T squared E bending star dot. And this is how the stretching energy at the minimizer changes with T, how the bending energy at the minimizer changes with T, and there's a minus sign between the two. The one grows, the other one decreases. Okay, now why did I get you through this? Is because when we saw this system, we thought it was driven by its metric. We thought that when this thing dries up, it developed some kind of a metric, and then things evolved to give us this helicoidal shape. And then we saw the following. If we take the system and slice thinner and thinner pieces of it, now by taking, not thinner, narrower ribbons of it, essentially I'm decreasing one of the length scales in the system, it becomes more and more twisted. Now when I'm coming to think of what I compare thicknesses to, here I compare thickness to this size, here I compare thickness to this size. This guy should behave thicker. This guy is effectively thicker than this guy. And it turns out that it is more twisted. In particular, it means that guy says this has less bending energy than this guy. How can it have less bending energy if it's more twisted? Exactly. What it wants to do is be twisted, by twisting more, it reduces the energy. So this is a way for us to uncover what these things want to do. We change the thickness, we disintegrate the object to tiny little pieces, and then we see what it wants to do, and that brings us closer to its reference state. Again, we have this energy. This is the metric in this case. It is flat and boring. It's the same as a sheet of paper. But the reference curvature, one is positive and one is negative. And we obtained that from the same architecture of a rubber bilayer we saw previously. And now we have two limits. In the thick limit, we are not willing... okay, let's go to the thin limit first. If we go to the thin limit, we have to be an isometry. An isometry of a flat geometry cannot have two curvatures. What do? You have to find a compromise. It turns out that the compromise is either obey this curvature or obey that curvature. It's a bistable system. Anyone know these toys that are slap bracelets? This is what it is. Okay, so you have two stable states, and that is in the thin limit. We obey the isometry, we have to compromise the curvatures. Notice what's happening here. Square root of t times the tangential curvature. This is the boundary layer which says, well, here you can develop biaxial curvatures because you're effectively thick. If we now, so this is thin, now we want to take this thing and make it thick. Because McMaster Cars only has, yay thicknesses available, the way for us to make it thick is cut it to smaller pieces. Okay? Compare its thickness to a smaller size. That effectively makes it thick. It behaves thicker. what you see here is you simultaneously obey both curvatures. But if you obey both curvatures, that means you inevitably compromised your metric. You'll no longer have the metric of a flat sheet of paper. Here you have pronouncedly negative Gaussian curvature. So those are the two limits. And contrary to what we saw in the previous case, well, the transition between the two was very abrupt. It was flat, 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 and then it puckered out of the plane. Here we have something else. When we're very wide, that is like being thin, then we're helicoidal ribbons. Okay, so what happens here is I'm not cutting along the straight line, I'm cutting at a diagonal of 45 degrees. Instead of being cylindrical, I'm a cylindrical helicoidal ribbon. I have a certain pitch to width ratio, and it plateaus here. And if I'm very thin, then I have both curvatures obeyed, and I look like a helicoidal ribbon, and it has negative Gaussian curvature. So this is the pitch, and this is the radius about which I'm rotating. And what you see is that there are two branches here. And we transit from the thin limit to the thick limit via this cusp. However, if you see that in the lab, then all you see is a mess of helicoidal ribbons becoming narrower and narrower and narrower, and you don't see that abrupt transition unless you try to plot one of these functions. So this is what happens when you're curvature driven. The other thing happens when you're metrically driven. And I think we can have a 5-minute break now, unless someone has questions. Good. So let's rejourn and talk about handedness soon. Yes?
Is it obvious that there's only a single minimizing configuration for the energy that is unique?
No, especially not in these systems, because okay, for the full-blown thing, yes, you can show that the left-hand portion, which is the stretching term, is a non-convex elastic energy, but it gets convexified by the second term, which contains higher derivatives. Okay, so the whole thing behaves rather well. But if I take just each of one of them in separation, they might not behave as well.
Higher derivatives?
Yeah, the curvatures are higher derivatives.
Yeah.
So that's one reason of saying that.
Because if it's not unique, then the less than, I mean, this argument may not make sense. Because you could have some situation in which at a different thickness you have, I guess, is that possible? If R star is not unique.
If R star is not unique.
The thickness and end up with the same R star.
Yes. So I was using this fact. Okay?
Yeah.
So take those and take the one with the least energy and say that is your global minimizer.
That's why you have the equal to.
Okay? And that's the global minimizer.
Could be
And
another. That's why
could be 5 of them. As long as you have something which satisfies this,
yeah.
you could pull out this trick. And this trick has to do actually with the shape of the functional, not with the fact that it's stretching or bending.
This comes to the fact that there isn't a t in front of the ES. Because when you subtract this equality from this inequality.
Yes, and I could have done everything with a parameter called tau, which is t to the minus 2, slap it on the stretching, and have monotonicity of that guy with respect to tau.
But you have a different sign.
And it's, I mean, when tau grows, t diminishes, vice versa. Okay?
And you got this by considering delta to be small, right? Or you'd have a
No, delta is whatever you'd like. That's the magic of it. So when you do this, this is what's fun about this thing. You could obtain something infinitesimal by doing this. Just saying the variation is such that the two balance out each other. You get this by saying this is the property of a minimizer.
Yeah.
It has less energy than anyone else. That's what it means to be a minimizer.
Right. Yeah. No, I agree with you.
And it will happen always when you have complete decoupling of the configuration and the knob.
Should it be E by T on both sides here, or
E?
well, it doesn't matter. So okay,
It's the total elastic energy. Yes, E over T.
so it doesn't matter
It's the same thing.
But doesn't this mean that minimum energy is convex? That doesn't mean that minimum energy with R star because of this? The minimum energy in the
Yes, I'm
space of
I'm
D and then
assuming.
R star.
Okay, it doesn't have to be convex in the sense that as long as this is L star, I'm good. Okay?
You just need a stable.
No. I need the one with the least. I need the global minimizer. This is the guy. So this guy won't work. A la what you said. This guy will work because I need to be able to state this.
No, but that is for a given thickness, right? I'm saying in the functional space of D and R star,
Yes.
the shape of this is convex.
Yes. No. Again, it could be this. This is for a given thickness and different R's.
Yeah, but in the space of D and R star, E will be convex. Because
No, E, you can show that E of E star, okay, you say in the space of R star and T.
yeah, not in the space of T.
That's a 1D, R star is a function of T, okay?
Yeah, so
So now you just have one knob, which is E, it's E star of T, essentially.
Okay.
E star of T is monotonous. You can show it. It's monotonically decreasing, that's it. So it's not convex, but it is convex, but it doesn't assure you convexity. It just assures you monotonicity.
And so, just going back to what you were saying here about chopping things up into smaller things. In some sense, you're given a problem of the C bar. You don't know a priori what the A bar and the B bar is. That's what you deduce by cutting it into little pieces.
Yes. So what I'm doing is,
Same limit.
I'm cutting it to tiny pieces.
Right.
I'm looking what it does in front of me. That's the reference curvature. Okay? That's the reference curvature. Now, try to deduce from that reference curvature and what it does intact, what's the reference metric. Now you're done. Okay? And the secret is to understand, now that I've cut it smaller, it's less constrained. But who am I seeing?
But I mean, can't you take the wide limit and just look at the metric then?
So what's done here is you understand when you cut narrower limits, then global constraints are relaxed. Okay, so what you should do if you want to get both the metric and the curvature is cut it to tiny pieces and now measure them and add them up. Okay? So if I now take a residually stressed glass that was shuttered and I measure all the distances,
Then you get
I get, pieces that don't fit next to one another, but they will make up this residually stressed object whose metric I can calculate by adding all these up.
with the spaces in between.
Yes. No, so I'm saying there's no spaces. I'm saying this face should be identified with this space. Can do it mechanically, but it should. And this has this volume, this has this volume, this has this volume. Now you get the whole metric. Okay? So that's it.
So from these experiments, can you get the real form of the metric itself?
Yes.
From the experiments you do?
Yes. Yes. If you cut really narrow ribbons, then you get
Just
something
the
which is.
stretching term and
Yes.
the-
Okay. Let's do this. Woo. This is way too much water. Yes. Ask about the tennis ball.
So if you flip it over, when you flip the tennis ball,
Yes.
we find that there's this flat region, and the flat region, the width of the flat region corresponds to the thickness itself, right? The width of the flat region corresponds to the thickness itself,
To the?
to the thickness of the tennis
No,
ball.
it corresponds to square root of the thickness over the curvature tangential to the boundary.
And how do we choose this? How do we choose L in that picture? L is the factor that we can.
This L,
L is something that you can.
we didn't know it in advance. We had to calculate what it was.
Okay.
Okay?
So it's not like you don't tune it over the whole.
No. So that's the width of the boundary layer. That's where everything came in, and we did a little scaling argument because they're fun to tell us what should L be. Okay? And the magic of these things, these are very robust. Anything you do, as long as you do your, keep your roughly Yeah, it's the right quantities in the right places. You get everything right.
In the graph that you showed at the end,
Yes.
what was the bottom branch for?
Width.
So that's the x-axis, but the two branches that you get.
Oh, the upper one was the pitch. The lower one was the radii. The radius about which you twist.
Oh.
Okay. 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 Yes. I want to.
Do you have time for one more?
Yeah, I want to perhaps erase these as we talk.
Wanted to figure out, yesterday there was a graph in which you have E versus area and
Yes.
two parts, one with constant aspect ratio and one with constant width.
Yes.
We're talking about the
Okay.
fractal.
Mm-hmm.
So I was trying to understand, don't you always have constant width because the leaf can't really change itself? Or
The what?
shouldn't the constant width branch be the...
No, because when you just start, when A is very small, A to the third is better. If A is small, A to the third is smaller than A. So that's something that you always have. You'd like to start isotropic. Okay? Okay. Okay. Okay, so let us continue.
I think this is sort of the heart of the frustration. A and B have to satisfy the compatibility condition.
Yes,
right?
they do.
And you minimize, you do that in your minimization. A bar and B bar
Don't.
and that's the source of the frustration.
Indeed.
If they could, they would stop.
If they could, the correct answer is boring. A equals A bar, B equals B bar, you're done.
And the energy is zero.
Yes. Okay. Okay. We don't have much time left. I tried my best to follow the motto Leo gave us. It's better to uncover a little than cover a lot. That means we have very little time left for this. But it's something that, again, is in the same spirit of what we were doing up until now when we were talking about geometric frustration in soft matter, where constituents would have enough size to have intrinsic structure. They would like to do something. And then they assemble or come together to give a complex system that in which those internal tendencies come to life or manifest in the global scale. And in order to do that, we have to be able to treat handedness quantitatively. And this is what I would like to do in the upcoming whatever time I have. So this whole portion now is going to be, a very dramatic change of gears and to talk about handedness. And there's a problem with handedness in the sense that it's a very, very intuitive topic. Here's a right hand. It's not complicated to discern this is a right hand. And here's a left hand, and they're mirror images one of the other. And I don't have to have the left hand in order to say that this is a right hand. And I don't have to have the right hand right side up to say that it's a right hand. Okay, now here's a troubling image. Now, it's troubling not only because of the grin on this guy's face, it's troubling because I put his right hand on his left-hand side, and I put his left hand on his right-hand side. And I did this for a point, just to exemplify that even on a daily basis, we use two notions of handedness. One of them is a cross-correlation of the right hand with the shape of my right hand. Whereas the right-hand side is surprisingly not determined by where your right hand is. It's actually determined by where your feet are and where your face is facing. So these are things we do on a daily basis. We use these two measures interchangeably, but we mustn't. As physicists, we also do this. We have two distinct notions of the right-hand rule. So one associates the direction of closure of the right-hand fingers with the direction of the thumb. The other one takes triply orthogonal ordered vectors. So I have A, B, and C. And if they're ordered this way, they're right. And if they're ordered the other way, they're left. Now, these are distinct notions. You can map them one to the other, either if you're extraordinarily flexible, or if you associate the transformation which takes A into B with the direction of closure of the right-hand fingers. Okay? So that's what we do in physics. And if you look at chemistry, there's another whole mess. But what all these things have in common is that they tell us if an object is right or left or neither. It doesn't even begin to tell us how left is this object or how right is this object. And if we want to be able, and this is the main driving of these kind of questions, what happens when I take left-handed constituents and bring them together and just self-assemble into this complex object? What's going to be the handedness of that object? What are going to be the handed properties of the response of that object? And these are the type of questions we always ask in soft matter. And in the context of biology, that is extremely important, because 19 out of the 20 amino acids that make us all share the same handedness. And that handedness essentially continues to manifest in almost every functioning piece of our life, of biological life. So unfortunately, these nomenclature type of recipes don't give us a quantitative measure. And what we'd like to do next is try to devise something which could be quantitative. And the first thing in achieving that is understand why is it hard to do something quantitative.
So this is a very interesting subtle question, but in the ancient times when this was discovered in sugar solutions, it was the rotary power of light at a certain frequency.
Yes.
So that might be, were you going to talk about that?
Yes.
Good.
Thank you.
So are we not supposed to start talking about responses? Or are they supposed to, or am I going to find out?
We will be able to talk about discrete collections of the points, and we would also like to be able to describe continuous bodies. It turns out the same type of structures would be able to capture both. We changed the details, but there's something which is more on the large scale I want to address first. Okay? So as David said, everything began essentially in the early 1800s. In 1811, Arago, which was a French scientist, only about 25 at the time, discovers optical activity in quartz crystals. Optical activity, also known as circular birefringence, is the rotation of the direction of linearly polarized light when it goes through a medium. So if I shine linearly polarized light, in this case at the principal axis of a quartz crystal, the direction of the light remains linearly polarized and it rotates. And the amount of rotation is proportional to the amount of material that the light has traversed. Biot, the same Biot from the Biot-Savart law, soon after begins to study optical activity of solutions, of gases, of liquids. And he discovers that many, many liquids, primarily with organic solutions, show optical activity. And there was one puzzle that came out about this time that entailed a lot of advancement afterwards, which was that of tartaric acid. Tartaric acid is one of the 3 acids in red wines that gives it the distinct taste. And sometimes we see crystals on the bottom of the cork. And when it's produced by wine lees and redissolved, it's very optically active. Now you can synthesize tartaric acid in a lab, and it turns out not to be optically active. So it's that's the essential puzzle. Now when you look at the crystals, they look very, very similar. And in terms of molecular structure, as far as they could tell, everything was the same. So what was different? It took almost some 30 years until Louis Pasteur, this is the same Pasteur which invented pasteurization and the vaccine for rabies and many other things, to discover that there was one facet in the crystals of tartaric acid when synthesized in a lab that was differing between different tiny crystals. And what he did is synthesize tartaric acid in the lab, solidified the thing into these tiny crystals, and then carefully sorted out the different crystals to the 2 types. Then he took those and redissolved them and discovered, then lo and behold, that now you have two solutions. Each is optically active. One is rotating light to the left, and the other to the right. And when you take the tartaric acid produced by wine lees, it produces just one of these. And then he goes on and reaches far-reaching conclusions about the handedness of life and how intertwined is in handedness and the ability to produce life. It is this setting of the 18th century, of 19th century, that we should think, or we should judge the only existing definition we have for handedness. And that was given in the Baltimore lecture by Lord Kelvin in 1893. And what he says is that I call any geometrical figure or a group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. So chirality, chir is just Greek for hand, is the lack of mirror symmetry. If something has mirror symmetry, it's achiral. If it doesn't have mirror symmetry, it's chiral. Now, why is this definition non-quantifiable? So first, there's some things that are puzzling. This is a 3-cup anemometer. It rotates counterclockwise whichever direction the wind comes from. I would really like to say handed things about this guy. However, a la Kelvin, there's a plane of mirror symmetry passing through all these rods, making this object achiral. So this thing, to some extent, a la Kelvin, is not handed. Optical activity. Turns out that there are 4 crystal groups that have mirror symmetry but can support optical activity. That means that, to some extent, even optical activity cannot be used to be synonymous with chirality. As a matter of fact, this specific Scotsman argued against the English dictionary to eliminate the terms optical activity from their definition of chirality, and eventually he won, and they did. So, to some extent, even optical activity is not intertwined with chirality. And last of all, this is more in our realm. This is a picture of an experiment done in Brandeis, this Vonimir Dogic group. And what we see here is a top view of a monolayer raft of colloidal rods. Each of these guys is about 1 micron long. They have an aspect ratio of about 100. They're very stiff, and they have some chiral decoration on them. That means that every 2 of them would like to stack slightly left-handedly with respect to one another. They stand up straight in the center. They curve to lie horizontal in the boundary. That's what stabilizes this raft. And you say, well, you know what? Every 2 would like to have a slightly leftward pitch. I guess that what they do is they do exactly that when they flatten out. You can examine that and show that indeed they do exactly what you'd expect. So you would say, oh, we can start thinking about self-assembly of handed objects. This is exactly it. And then if you just reduce line tension, so this whole system is driven by depletion interactions, and if you reduce the amount of depletants, essentially allow this to have less surface tension, then it develops undulations. And these undulations develop into tentacles, and each one of those tentacles becomes a glorious helicoidal ribbon. Only each and every one of those helicoidal ribbons is right-handed. So to a very large extent, not only we don't get the numbers in, we can't even get the sign right. And this is what we would like to address. In discrete systems, in continuous systems, we first want to understand what's happening here. And the main hurdle, I think that the main impediment towards quantifying handedness appropriately is this. When we think of the group of left-handed objects, we think of it as being distinct from the group of right-handed objects, and they're separated by the group of mirror symmetric objects. So for example, if I have this guy, and I want to map it into its own mirror image, then I have to do this. And just for a brief moment in time here, it had to go through the group of mirror symmetric structures. Okay, so this is this mapping. It turns out that without much effort, we can do something else, which is just splay 2 rings aside, then invert the other 8, then take the other 2 back, and bring them together. I just went from here to here without ever passing through a mirror symmetric configuration. It turns out that not only phase space looks more like this, it turns out that it's not clear that there is a clear separation between left and right. This notion was made formal by Kurt Mislow and Weinberg up in '97, and what they showed is this is called Cairo Connectedness. And they show that this is possible whenever your amount of degrees of freedom in d dimensions is equal or larger than d plus 2. So that's essentially everything, almost. So how should we start to understand these structures? Yes, please.
So this, you're just thinking of this spring as one dimension. You don't, because in real life, if I had a physical thing, a two-dimensional cross section, there would be some twist that I have this function.
Idealized. A mathematical spring, completely shearable, couldn't tell. It's a line. It's an idealized line. Okay. So here is our famous bilayer, which has been with us in each and every one of the lectures. And here we take a diagonal segment of it. And what we should observe now is that it's right-handed. Okay? And now what I'm going to do is I'm going to slice a small piece of the top of it. Okay? So as I slice, it twists, only it twists left-handedly. And you can take a full right-handed ribbon and disintegrate it into very tiny right-handed smaller ribbons. So this is the system we're examining again. This is again trivial metric hyperbolic curvature structure. It's this layer is stretched this way, this layer is stretched this way. Now they're glued one onto the other. And now what I do is I take narrow ribbons. Why do I want narrow ribbons instead of wide? Yes, because I want to compromise the metric and manifest the curvatures. So I cut narrow ribbons. And if I cut upper right diagonals, I get right-handed ribbons. And if I cut upper left diagonals, I get left-handed ribbons. And the continuum structure we started from, if you examine this thing and you ask, what are the symmetry properties of this thing? It has lots of symmetries. In particular, it has mirror symmetry. So the continuum structure, underlying structure, has mirror symmetry. The only symmetry broken is by the boundary conditions. So it does not surprise us that aspect ratio determines everything. I can take something with an aspect ratio of 2, and it's going to be left, and slice from it something of an aspect ratio of half, and it's going to become right. Okay? So that part is sort of understood. But what happens if I take something of an aspect ratio 1? Well, I can't say if it's right or left, so it's got to be mirror symmetric, and indeed it's mirror symmetric. But now I take 6 copies of this guy, which doesn't have any handiness because it's mirror symmetric. And I flatten them and I glue them one to the other, and I can make up this guy, which is right. Where did the handedness come from? I can do the same trick again, take another 6 copies, flatten them down on a table, glue them one to the other, and I can get this guy. Again, where did the handedness come from? And when you judge this guy in context, you understand where it came from. Because I can seamlessly continue this guy into this right-handed guy, and seamlessly continue it into this left-handed guy, only I do those in perpendicular directions. Now, if there's any underlying potency of this guy, I would like to say that not it doesn't have handedness at all, but that it is right-handed along this direction, and it's left-handed along this direction. In particular, what I'm trying to do is take something which is mirror symmetric and assign handedness to it. That tells us that we don't know what handedness is. And then we go back to the scratchboard and say, what are all the chiral phenomena you know? Either chiral propeller, the right-hand rule, optical activity, thread handedness, handedness of organic compounds, and what all these handedness notions have in common. But what they do all have in common is that they all relate directions to rotations. So why not use that as the origin of handedness? In general, in 3D, a direction is a vector. A rotation is a pseudo-vector. So when you relate one to the other, what you'll require is a rank 2 pseudo-tensor. So this is what I would like to say handedness should look like. And the reason why some objects, okay, so this is a general handedness. Now, if we now stop for a moment and go back to the context of the 19th century, solutions of isotropic solutions of constituents, then essentially what I should take is isotropic averages of this guy. So each and every one of my constituents, I say, has this kind of handedness. But if you average over all orientations, what you get is this kind of an object, where C is proportional to the trace of this chi. It's very easy to show that if your object is mirror symmetric, the tensor properties or the pseudo-tensorial properties of this say that this C has to vanish. Okay? So the path says that if you have a mirror symmetric structure, its isotropic averaged handedness has to vanish. So to that extent, we reproduce Lord Kelvin's notion of handedness, but we no longer, with modern technology, judge only isotropic collections of objects. We judge single-oriented objects and judge their response. Particularly, it tells us that if we have the full structure, we don't have to average it over. We can judge just one direction. Some objects have handedness which are very easily discernible, like this right-handed spring. Why is it so easily discernible? Because it has an axis going along its length. And what we do is we use that axis to single out just one component of this tensor. What we're going to do next is take objects to which we could easily associate handedness and understand that what we've been associating with their handedness up until now was one component of this tensor, and try to generalize it into a general tensor. Okay, so that's and the game played is who's the rotation, what's the direction. Once you're able to isolate those two, then you can construct this pseudo-tensor. Okay, this is a right-handed helicoidal ribbon. What did I do to discern that it was right-handed? Okay, so I get many of these. Essentially what I'm doing is what I did. Every one of us has a different version of it. Is I was doing this. What is this? I'm following the tangent of the surface. I'm essentially following the orientation of the normal of the surface along the long line of the surface, and I'm asking how does it rotate about that same line. So that's the rotation and that's the direction. Now I can ask this question about every possible direction, and I can ask this question about every possible rotation. And that is the following recipe. You give me a direction, I project it to the surface. So that's the first part of the recipe. Now I go along that direction and ask how does the normal rotate. And I don't take just one component of the rotation, I take all components of that rotation. In component form, it reads this. This is the metric or the inverse metric of the surface. This is a tangent vector. This is Levi-Civita. This is normal and normal derivative. We can show that these Levi-Civita normal derivative are questions about how does the normal rotate. I'm taking only the component of differentiation which points along the leg J. I do this by this machinery. I don't want to get into the details. We don't have the time for it. What's really important here to take home is that if you give me two unit vectors, m and n, this contraction, m chi n, tells us how does the normal rotate about m when displaced about the projection you got from n. This is this, but in all directions simultaneously. Now, this is a density for every point in the surface. We can generate it, integrate it over the whole surface and get this thing. And we can calculate it. We can calculate it for this object. This little piece was mirror symmetric. So it has a traceless handedness tensor. And in particular, what we see here is that while for a pseudoscalar, if I tell you that an object equals minus itself, essentially that it's mirror symmetric, it has to vanish. For a pseudotensor, this is not the case. So this tensor is its own mirror image, and it's non-vanishing. This guy is not mirror symmetric. You can see that it's not its own mirror image. Its mirror image is this guy, which has a minus here. So if this is the x-axis, I see a lot of right-handedness along the x-axis. I see a lot of left-handedness along the y-axis here. We fairly understand well why this guy is traceless. Quite surprisingly, these guys are traceless as well. For a while there, we thought that this was something wrong we did, so we took a whole bunch of other surfaces and explored their trace, and turns out those are 0 as well. So you can cook up another measure. By no means am I saying there's one handedness measure that is good for everything else. All I'm saying that you can cook a zillion of different measures, but they all need to be orientation dependent. This is another measure that comes from Stokes flows. It gives different tensors, and again, for surfaces, they all are traceless. Turns out you can...
Just a naive question. Couldn't your definition be scale dependent? Because if I were to make up your strip or something of constituent molecules themselves having rotary power or shape, and I have a macroscopic chirality which is small scale chirality. And I suspect with rotary power, it's frequency dependent. It's the same kind of thing.
Yes, okay. Unambiguously right. It could be scale dependent, so this chi would, on top of everything else, be chi of k, and I would be probing finer and finer structure of my object. Nonetheless, it would still have to have this spatial dependence in exactly the same way. It would still have to be a pseudotensor of this shape. So there are many different types of these, specifically size dependent or scale dependent, but they all have to have the same framework. For the specific context of smooth surfaces, it turns out that you're able to prove that a leading order handed contribution to the tensor for these guys is always traceless. It comes from the fact that if you're trying to describe surfaces in terms of the first and second fundamental forms, which we know suffice to reconstruct a surface, then what we have is essentially a structure which has two mirror planes. The principal curvature direction and the direction of the normal generates a plane about which the intrinsic structure of the first and second fundamental forms can be mirror imaged. So locally, the structure which is described by the first few derivatives of a surface is always mirror symmetric. If you go to sufficiently high derivatives, this is going to break. But the first few orders is always going to be traceless. So this is something which is unique to surfaces. If we now try to take the same logic, we can generalize it to director fields. Say, how does a director field n rotate about the leg I when I translate it along the leg j? This is an object whose trace is the helicity of the vector field n. So it's n dot curl n. In particular, if we have a cholesteric order here, slapping this machinery on the cholesteric order, it would automatically tell us not only the cholesteric pitch, but also the cholesteric direction. If we now take a curve in space, so a curve in space would be characterized by a curvature and a torsion, and we ask again the same question. How does the normal to the curve rotate about the direction I when I walk along the curve in the projection from J? That's the game played, and it turns out that you get this tensor, which has Ti Bj, this is the tangent and this is the binormal, times kappa, the curvature of the curve, plus tau, the torsion of the curve, Ti Tj. The trace of this object, chi I, it says Ti Bi, that's the dot product between T and B that goes to 0, and you just have tau. So this again could be traceful. However, every time we consider surfaces, we get a traceless contribution. Can we see this? Can we see this in experiment? Can we see this in real-life systems that are simple? So this is perhaps the simplest way to see it. I 3D printed me a helicoid. I'm a theoretician, so it's 5 centimeters long. And then I printed it a twin that has the same structure exactly, only it's hinged along the perpendicular direction. this is a standard view just to make sure that it's the exact same guy. And now I put it in an airflow. So air comes from the left. It gets deflected by this right-handed helicoidal ribbon to the right. So the object rotates to the left. This does exactly what I would expect it to do. Now when I do it for this guy, not only it rotates this way, the other way, it does so faster. If I had to now tell you this is the x direction, this is the z direction, what does the y direction do? Does it rotate the same way as the z or the x?
X.
Who says x? Who says z? Okay, participation ratio low. So if we bear in mind the notion of tracelessness, which doesn't have to hold here. This is high Reynolds number flows. Everything is very messy. But there's some signature of that underlying notion. Then everyone has to average out to 0. So we need 2 of these to balance that guy. That is indeed what we see. This also begins to explain to us why don't the chiral rods we see here stack in a left-handed fashion? We saw this right-handed helicoidal ribbon, and we said, well, this is the wrong sign. What we know now is every time we see a surface-like structure manifesting handedness, then when we say it's right-handed, what we actually say is it's right-handed along the length. And in particular, it has to be left-handed across the width. And if we now follow the progression of the rods between this side and that side, we see that they do stack in a left-handed fashion, only they do so in an unexpected direction. Okay, so now this assembly process, we should judge it in an oriented fashion, because handedness is invariably an oriented property. So what we first do is we stack rods along this direction. We make these small twisted platelets, and then take those and stack them up. So with the aid of a colleague, Rasko Stepnek, we did these MD simulations in which we took these slightly left-handed platelets, which are to mimic the cross sections of these guys, and then put them in a container with depletion agents, and let them make a surface, and lo and behold, they make a right-handed ribbon. So the minute we start to judge the handedness self-assembly processes in an orientation-dependent fashion, then we're able to start treating things quantitatively. However, we lose the ability to say about things that are just right-handed. They have to be uniaxially right-handed, or right-handed along the x and left-handed along the y directions. So questions about these so far? Yes?
I thought that phenomenon depended upon the pitch. I mean, if you think of the viruses that have the twist of the then the twist of the global structure depends upon pitch.
The ratio of the pitch to essentially the pitch angle.
Yeah, the pitch angle. Right?
The pitch angle. So that notion dates back to Straley. And what was happening here, it's a very high pitch angle, if you'd like. And you can show that every pair would like to self-assemble into a left-handed assembly. Nonetheless, when they make ribbon, they make a right-handed ribbon. So even with that consideration, they do the wrong thing. Actually, they do the right thing along the surprising direction. What I'm working on now is see if we can formulate Straley as owing to the directionality of the handedness in a single constituent. So can we formulate that in an orientation-dependent way? So I think we're about out of time. What we've been through in the last 3 hours, last three lessons, is primarily frustrated elastic structures. We discussed the notion of geometric frustration. We did so in liquid crystals in the context of growth and of irreversible deformations. And we formalized the description of frustrated objects through Riemannian geometry. When we did that, we discovered that frustration was almost inevitable in spontaneous systems, spontaneously forming systems. And then we used that formalism also to help us distinguish via elasticity between geometric frustration and residual stress. We saw that while geometric frustration was something we could quantify locally, residual stress, or the way of resolving that frustration, could be global, could care about things like the aspect ratio of my system, could care about things like how big my system is. And then we took all this discussion, which we did in 3D and 2D, and also did that in thin sheets. And I think the most attractive reason to do that in thin sheets is because of things like that, because little goes a long way. Thin sheets are easily deformable, and therefore very small strains can manifest as very large deformations in real space. And that allows us to observe all the richness this phenomena can show. We discussed orientation-dependent handedness measures and handedness in self-assembly. And all these things have in common the thread that they have to do with intrinsic tendencies of the constituents of material and how they come together to manifest in the material as a whole. The one thing I want to end with is to put this in context. And one thing I at least try to do in schools is to make sure that I talk about things that I think are basic, and you know, the metric description of elasticity dates back to the 50s. But as a matter of fact, if you take frustration in liquid crystals, give me an arbitrary torsion field, bending field, and splay field, it is presently unknown in 3D what is the compatibility conditions. Okay, so these are that's where we're at now. In the context of handedness, there's still a lot to cover. In particular, there are 3-point correlation functions of handedness, and there are 4-point correlation functions of handedness. The first vanishes. The first has a pathological zero trace. Unfortunately, those are the ones we know how to construct. The other one vanishes for mirror symmetric structures. We show in experiment that we have to have both. What is the relation of the one to the other is still something we're working on. So all these things are, on the one hand, very old, but on the other hand, at the frontier of the soft matter research we're doing. Thank you very much.
So what camera do you use to make those movies?
William, what camera did we use to film the rotating? It was a Phantom. I think that was filmed at several thousand frames per second, so it's not dramatic. I think something like 5,000. What? About 1,000.
So using the machinery of this, like the hyperelasticity.
Okay.
Can we understand why potato chips sort of like bend when you toast them?
So when we first wrote the paper about the hydrogels, Randall Kamian wrote a perspectives on it, and the cover image on that was that of a Pringle.
Oh, really?
So a potato chip, not a Pringle. Pringles are cast. A potato chip has to be fried. In our language, what we would say is that the frying does not break up-down symmetry. Okay?